Thank you very much. I like to thank Noam and Huang for the invitation. So this is my fourth time to ESI. So it's great to be back. And so last year we had a conference called the Generalized Computability Theory in Spain, and I enjoyed it so much. And this time, of course, they asked if we would like to come back. And so I said, yeah, sure. But last year, at least I gave a talk about proving something about the effective descriptive set theory, which is a sort of a generalized computability theory topic. But this year, I thought about it. I didn't have anything like that. So, but this is something I've been working on. Borel combinatorics has been something I've been working on for several years, or many years, I think, 15 years. But I try to use this talk to make a point, which is you don't go find computability theory. Computability theory will come and find you. So you'll see, we were interested in something that is completely unrelated, and then something came up that turns out to have something to do with computability. So once again, this has been a long-term collaboration with some people in North Texas. Steve Jackson and a couple of students back then. One of them is Ed Krohn, who's no longer in academia. And Brendan Seward has since moved out of logic into geometric group theory, and he's now at UC San Diego. But anyway, this has been our joint project for many years. And so many of the results, not all, but the majority of the results in this talk are our joint results. So let me just tell you what kind of combinatorial problems or Borel combinatorics that we're interested in. First of all, there's the combinatorics we're referring to is about graph combinatorics. So a graph, everybody knows, it consists of vertices and edges. And then over there, one of the main combinatorial features that we care about was the chromatic number, which is to say how many colors do you need to color the vertices of the graph so that adjacent vertices are colored differently, right? So this is a graph theoretic notion. And similarly, there's a notion of edge chromatic number, which is this time you're coloring the edges rather than the vertices, so that so-called adjacent edges, like edges that share a node over there, will have different colors. So this is a kind of also a notion that is studied a lot in combinatorics. And one other notion, which is, I'm just giving you an example of another notion, which is perfect matching in the graph, is a set of edges where it talks about every vertex. Every vertex is matched to another vertex. And so this is called a perfect matching. And so in this talk, I'm not going to, and there are many more combinatorial problems. But in this talk, I'm going to focus on chromatic numbers in general. But in the descriptive set theory context, we need to put definability on these graphs. So first, I want to just, an intermediate step is to talk about the topological graph, which is a graph that is situated on the topological space. So there's a topology on the vertices, and therefore a topology on the edges as well. So in this case, you can actually talk about the so-called continuous chromatic numbers, because that coloring function to assign colors to the vertices is just a map from the space to some sort of space of colors. And the space of colors will always equipped with the discrete topology. So in that case, you can talk about the continuous chromatic numbers, because these maps are just the maps between topological spaces, and therefore you can just say, oh, is there a continuous such a thing? Okay, and as logicians, of course, we like to figure out, like, when you put definability conditions on things, what happens, right? And as suspected, these things will behave very differently from the general chromatic numbers. If you don't have any definability restriction over there, you'll get very different answers, okay? And also, edge chromatic number, you can also talk about continuous ones. Perfect matching in that case, you could talk about the clopen, open, Borel, this and that. So all of these notions. But then that was the intermediate step when you put a topology on the graph. But in general, you could also go further, which is to just to put a Borel structure. So when we actually put a standard Borel structure on the graph, and you can talk about all of it. That's the context of Borel combinatorics I'm interested in. Okay. So here we talk about Borel chromatic numbers, Borel edge chromatic numbers, Borel matching, etc. Okay. So so this is the general context. Now you can even go further and talk about a bare measurable, Lebesgue measurable, or you could, instead of going up, going down, you can talk about a computable, you can talk about the effective Borel, which is delta 1 or height, or any other notion, right? So all of this, you can, in other words, you can study combinatorics in all this different contexts. Okay. All right, I'll just give you one quick example of the kind of chromatic number question, which will have different answers under different definability assumptions. So, so just to consider a so-called, this is so-called irrational rotation, right? So you think of the circle space as a copy of 0, 1, you know, with 0 and 1, you know, glued together as a single point, and then here. The equivalence relation that I want to consider is if two points over here, if they differ, you know, if their angle differ by an irrational number, some sort of irrational number alpha, okay? So if you think about that, so you start at one point, you rotate alpha, and then you rotate alpha again, that becomes a dynamical system, and the orbits of this, you can put a graph like over there by every time you rotate alpha, you connect the two nodes. Over there, obviously, if you focus on each orbit, it's just a line, okay? Going forward and going backward infinitely. So it's a bi-infinite line over there. So every point, in other words, every point over here is connected. Every point over here is connected to the next point, which is angle alpha away from it, okay? And then say clockwise or counterclockwise, whichever, and do it again and iterate it. Okay, so so every connected component is just looks very simple. It's just a line over there, and the chromatic number is very obvious. It's just 2, because you just color them 0, 1, 0, 1, etc. Okay, edge chromatic number is the same thing. But of course, if you talk about the continuous chromatic number, is actually undefined because this space is actually a connected space. It cannot be mapped in a continuous way to a discrete space with more than one element, you know, with more than one element in the range. Okay. So anyway, so if we modify it slightly, which is we take off one orbit over there. If you think about it, if you have an irrational rotation, then every orbit is dense. So it's a sort of a copy of a rational number or something, right? You take out one orbit over there, then there are infinitely many holes, okay? So this new space now becomes a zero-dimensional space, and then we can talk about the continuous chromatic number without having that kind of triviality of the connectivity. So over here, every connected component still looks like this, and the chromatic number and edge chromatic number of this is still 2, like before, you know, because you focus one point, on one point you just say, I color this 0, I color the next one 1, etc. But this time it makes sense to talk about the continuous chromatic number, and it turns out, like I mentioned, it turns out that you can use an argument using Lebesgue density or a Bernoulli category to argue that you cannot put a continuous coloring on this thing with 2 colors, okay? Because it's a very simple argument using Lebesgue density or Bernoulli category. And it turns out that this continuous chromatic number and the continuous edge chromatic number is just, they're both 3, okay, instead of 2. So this is already like the difference between putting a definability condition on the graph and not putting a definability condition, then you get different answers. Okay, so and one can easily see that that of course this if you can put 3 colors, on that edge or vertices in a continuous way, then you can put it in a Borel way. And in fact, this argument that the chromatic number cannot be 2 in the definable setting also applies to Borel setting. Okay, not just the continuous. Okay, all right. It's a very simple example over here, but in general, our examples come from the so-called group actions, and these are so-called marked group actions. What are they? A marked group is a countable group with finite set of generators specified, whichever is the generator we want to know, is fixed in advance. So this is a finite set of generators that are in general, I assume them to be symmetric. Like if one generator is there, then its inverse is in there, and they do not contain identity. Okay. So once you have such a marked group, it has this KD graph, which is the usual thing. Like an edge in the KD graph is just connects two group elements, which are in this particular case, I use right multiplication by a element of the generating set. Okay. So for example, here's an example. In Z squared, if I look at the generators plus minus 1, 0, and the 0 plus minus 1, I got this lattice thing, okay, which is a, in fact, you don't need both plus and minus, but you got the same thing, because my assumption over here is that the generating set will be symmetric, and therefore you get this. And in general, of course, you have, these are group elements that I'm drawing over here, and in particular, I drew the origin over there. But in general, if you just care about the graph itself, it doesn't matter where the origin is, okay? Because they look the same. Okay. But if you change the generating set, you will get very different graphs. So, for example, here is a generating set that is augmented, but by the new generators plus minus 1 plus minus 1. So this is the new graph, and it will have a different chromatic number and different edge chromatic number, etc. Okay, so then the previous one. So these are the things that we're interested in, and then once we have the group, mark the groups, we consider their Borel, the so-called Bernoulli shift actions. So the Bernoulli shift action, the space is actually 2 to the gamma. If the countable group is gamma, then the space is 2 to the gamma, which is you put a 0, 1 label on the group elements, you form this new space. The 2 to the gamma is a polar space, perfect and everything. And then you shift these elements by the group elements, okay? So here I'm using the right shift over here. Is an isomorphic copy of the, if you are used to the left shift is equivalent, okay? Here I just want to avoid writing inverses. And then once you have the KD graph, once you have this action, then the KD graph can be imposed on the space, on each of the orbit over there. And this is called the Schreier graph in the literature. So the Schreier graph, in other words, are the 2 elements of 2 to the gamma now. And then these elements have an edge in between them if there is a generating set, an element of the generating set that acts on one element and gives the other one. Okay. So, but in particular, so we're interested in, for example, if you have groups that are 2 to the z to the n, z squared, etc. Fn is a free group with n generators. All of these are, group, actions, and so you can consider the Bernoulli shift actions on them. What are these Fs? These are the so-called free parts. So the free part of the Bernoulli shift action is the part where the action is acting free. Okay. So why are we interested in that? Because on the free part, the copy of the Schreier graph over there looks exactly like a copy of the KD graph, okay, because no 2 nodes are identified as the same one over there. So So this is the general context where we're interested in doing our Borel combinatorics arguments, okay? And I'm drawing the Schreier graph on this free part of the space 2 to the z squared, where the acting group is z squared because I'm talking about free action here on this part. So the Schreier graph looks exactly like the Cayley graph we have seen before, okay? But this is only one orbit, like one part of one orbit, but there are continuum many orbits over there, right, in this space. So then you can ask the question about the Borel combinatorics, continuous combinatorics, etc. Okay. So the question here is, what is the chromatic number of the Schreier graph on f up to the z squared? This was actually one of the questions asked by Tekris, Selesky, and Todorshevich in the 1999 paper. As an open question back then. So the easiest answer is with AC. If you don't care about definability, the answer is 2. That lattice over there is like a checkerboard. Then you put 0 and 1, diagonally. Then then it's a coloring. But one can prove, similar to the one-dimensional case, that there are no bare measurable or Levig measurable proper 2 colorings on this thing. So the Borel number or chromatic number, continuous number, etc., they're definitely not 2. Okay. So what are they? Well, so one of the earlier, well, it's not one of the earlier, but this result has come out for. We eventually proved that the Borel chromatic number is 3. Okay. And this uses a lot of mechanisms. We have to invent something called orthogonal marker constructions. And in fact, our original proof was still unpublished, so it's being submitted in the paper. But on the other hand, the continuous chromatic number, one can study this, and we proved that it's exactly 4. Okay. So you can put 4 colors in a continuous way on this thing, but you cannot use less than 4 colors if you just care about the continuous ones. So these are the kind of questions and answers, okay? What does it have to do with computability? Well, it's because that in general, okay, so there's a similar thing about the edge chromatic number. We have similar answers over there. With AC, the edge chromatic number is 4 because everybody has 4 edges. So you need at least 4 colors to color the edges, okay? But here's a lot. 4 different groups of people who actually proved that the Borel edge chromatic number is exactly 4. Okay, and so this problem got a lot of attention, and we proved that the continuous edge chromatic number, on the other hand, you need 1 more, just like the chromatic number case. So these are some examples of the kind of questions that we have been interested in and been working on for at least 10 years. But today, what I want to talk about is, like, you can actually put a bigger framework on this type of problems and say all of these problems are just special cases of this big framework. And this big framework is called z-squared subshifts of finite type. I'm going to use this z-squared as a particular example, but you can actually do this for other groups. Okay. So what is a z-squared subshift of finite type? It takes us several steps to make this definition. So first of all, you look at the z-squared as a lattice, like we just have seen like a couple times. First of all, I want to talk about a pattern, so-called a pattern. A pattern is a partial function with a finite domain, okay, to some kind of, target space. Okay, this target space is finite also. Okay, so you can think of the domain of the pattern is always, without loss of generality, you can think of the domain of the pattern to be a rectangle over there. Okay, so it's always like a 0 to k minus 1 kind of assignment on a rectangular, lattice over there, and that is a pattern. Okay, so a pattern occurs in some element, in some infinite element, is like you can find a place where you can recognize the pattern over there, okay? And then a subshift of finite type is that you specify finitely many patterns over there, and you say, I don't want to see this. So these are the so-called forbidden patterns, okay? So P1 through Pn, you specify n many forbidden patterns, and then you look at all of the elements of k to the z squared, okay? All ways to put labels on z squared lattice where the patterns do not occur at all. Like no matter where you look, you don't see the pattern. So this is the so-called subshift of finite type. This space, one can easily check. This is a closed subspace of the k to the z squared, this bigger space. And therefore, it's a good Polish space and everything. And also, the shift action doesn't change. In other words, this space is the invariant space for the shift action. Okay, if you don't see the pattern, you shift it, you still don't see it. Okay, that's what it is. So this is a subshift of finite type definition, which was studied a lot in dynamical systems, symbolic dynamics. But then I'm going to argue a little bit that these chromatic number questions are actually certain questions that are related to these subshifts of finite types. So here's the thing. So suppose we ask the question, is there a continuous proper three coloring of this? Like, because we answered it. Remember, if you remember, our answer was that no. The answer is no. There's a continuous four coloring of this guy, but no continuous three coloring. That was our answer. Okay, but suppose that we are just basically interested in this one question over here. I'm arguing that we can turn it into a question about the subshifts of finite type. So so consider this a z-squared subshift of finite type, which is a subset of 3 to the z squared, 3 referring to 3 colorings. Okay, putting 0, 1, 2, 3 colors on those lattice points. Okay, where the forbidden patterns are, all those, like I listed 6 forbidden patterns, all of them consist of nodes that are adjacent to each other but having assigned the same color. Okay, those are forbidden. And other than that, if you're not seeing this, then it's a good 3 coloring. Okay, so then with this understanding, the question whether there's a continuous 3 coloring becomes an equivalent question, which is whether there is a continuous equivariant map from that free part of 2 to the z squared to this guy, to this subshift of finite type. Okay. If there is, then you have a continuous recovery. If there is not, then you don't have it. Okay. So this is like a general framework, because if you think about this, here I'm giving the example of just a chromatic number, but if you think about other examples, edge coloring or matching or these other types of combinatorial questions, many of them can be put in this bag over here. Like they are special cases of the kind of question whether there's a continuous equivariant map from this guy, from this space that we're interested in, into this space of finite subshifts of finite type. Okay. So equivariant here means that is a very algebraic thing, like because these are 2 shift spaces, because z squared acts on both of these. So here we're just saying that you act on, you let an element act on something and you send it to this. It's equivariant map if it commutes with the action. Okay. So the next example, I'm going to be quick and skip it a little bit, because basically I'm just saying that if you consider the edge chromatic number question, you can do it again. Like basically here, if I say, is there a proper edge 5 coloring, you can actually design something over there by saying that, I can specify that by designing some forbidden patterns over there. So I'm going to skip this. But if you trust me that this problem is more general, okay? Given a z-squared subshift of finite type, is there a continuous equivariant map from this free part of 2 to the z squared 2x is, many of the questions that we are interested in combinatorics boils down to something like that. Okay. So, and then now we have lifted the whole questions into a new framework where all of the questions are special cases, and now we're going to try to give a sweeping answer to all of that. To say that, okay, you want to answer this, I'm going to tell you what the answer is. But unfortunately, it's a theoretical answer. Okay, not so practical yet. Okay, we give a complete answer to this problem. We refer to this as a subshift problem. The complete answer is the following, which is what we call the 12-tile theorem. First of all, I'm going to state the theorem, which is to say that there is a whole bunch of finite graphs. These are graphs, what we call the G, N, P, Q. So there are 3 parameters, N, P, and Q. These are natural numbers. N is less than P and Q, okay? P and Q are actually, for our practical purposes, P and Q are coprime, okay? So a whole bunch of such graphs that will determine the answer to our sweeping problem, which is whether there is a continuous equivariant map from this guy to X. Remember, all of these special questions are special forms of this type of things. If and only if there is an equivariant map from the finite graphs, the G, N, P, Q, to X, for some sufficiently large, like for some N, P, Q, where N is less than PQ, and P and Q are coprime. Okay, so these 1 and 2 are equivalent. All right, so 3 says that for all N and for all sufficiently large P and Q, then there is an equivariant map from this finite guy G and PQ to X. Okay, so in view of time, I'm just gonna browse through, give you a very quick introduction of these finite graphs. These finite graphs are constructed in multiple steps. Okay. First of all, I'm gonna try to define G and PQ. Okay. Remember that the N, P, Q are parameters over there, and the P and the Q are larger than N. So the definition of this graph over here, G and PQ, consists of several components. These components are called tiles, and there are altogether 12 tiles with each tuple, NPQ. There are 12 tiles. There are 4 so-called torus tiles, 4 so-called commutativity tiles, 4 long tile horizontal ones, and 4 vertical ones. Okay, two of each. So the torus file, I will just say very quickly that every tile is a finite lattice graph. Okay. Except that we just specify certain parts of the lattice. For example, the 4 corners over here, they are n by n. So Rx is n by n. And then RC over there is RC is just a label. The RC over there is the length of it is P minus n, and then the height of it is n. Okay. So then RA is the opposite, okay, etc. So these are torus files. I give these labels over there because eventually I want to identify the vertices with the same labels. Okay, so in other words, I'm going to just go through this quickly, and later on there's a more depicted example over there, which might be easier to understand. So these are called torus files with various different dimensions. Torus files, 4 of them. Commutativity tiles, it's called commutativity because on the upper edge, there's a RD and RC over there, and on the lower edge, there's a RC, RD, the order reversed, and similarly for the other ones, A and the B reversed, etc. So there are 4 commutativity tiles. Long horizontal tiles are a whole bunch of RC on the upper edge and a whole bunch of RD on the lower edge. They're of different dimensions. Because RC is, each one is P minus N long, okay? And the RD is Q minus N long. So they're of different length. So you can calculate like how many RCs you need in order to actually, for this whole thing to work out. This is the horizontal tile and then the vertical tiles. So here's a better example. This is G1, 2, 3, okay? So n is 1, okay? P is 2, and therefore P minus n is 1, and the Q is 3, so Q minus n is 2. So over here, the first torus tile is just a 3 by 3. I colored the corner ones because these 4 corner ones eventually will become one node. Okay, you just take a quotient of this. Like all of these nodes with the same colors, they're going to be, except for the white ones. The white ones are the unlabeled ones. Okay, the white ones will stay themselves, but the ones with colors, they will eventually be, made the single node. For example, all the green nodes will become one node. Okay, all the orange ones or the light orange ones, etc., etc. Okay. So the black nodes, in particular, all on the corners, they all will become one node. So this is what the G1, 2, 3 tiles. There are 12 of them. Here are 4. Okay, and then the next 4 looks like this. Okay, and the next 4 look like this. Okay, so I have specified the 12 tiles. Now you do this identification process. You got a single finite graph over there. That's called the G1, 2, 3. All right, and of course, because the way that we constructed over here, from every node, if we move to the right, that's actually plus 1, 0. Okay, acting on it, and if you move down, that's 0 minus 1 acting on it. Okay, so so this is all 12 tiles putting together in this graph over here. Okay, and then once you identify all the tiles, all the same color nodes, then you got that G1, 2, 3. Okay. So the 12 tile theorem, I'm repeating what I said over there. Is like whether there is a continuous equivariant map from this, my question, it is equivalent to whether there is some kind of MPQ, okay, so that you can actually put this K colors on there, so that these finite subshifts, the subshifts of finite type X over there. Here is when I say theta respects this X, it means that you don't see that pattern. You don't see the forbidden pattern when you put this finite, when you put the patterns on the finite graph over there. So this is why I'm saying that the computability theory comes to you. Now you can see that this notion over here in 2 or 3 is just our CE, okay? With respect to the MPQ parameter, okay? So basically that proves that the question whether there is a continuous equivariant map from f of 2 to the z squared to x is just a CE question. Okay, it's sigma 0, 1, light phase sigma 0, 1. Okay, but the next thing is I just want to say that it is possible to prove that this is sigma 0, 1 complete. Okay, it is not computable. So you can quickly, I'll just say that you can actually code. So I'll just, you can actually code this word problem, the word problem for finally presented torsion-free groups. Okay, it is known to be undecidable, but you can code this problem. This is what we did. I'm sure there are many different ways of coding undecidable problems into this problem over here. But this one thing that we did was to code the word problem for finally presented torsion-free groups into this problem that we care about. Okay. So anyway, I think that I'm going to just skip the next few slides over here because this gives the details about if you start with the word problem, how do you make it? How do you make a subject of finite type? What are the forbidden patterns, and how do you make it? This uses a lot of mechanism. So our paper is about 120 pages. Anyway. I'm going to skip all this. Okay. What about one dimension? So I just talked about 2 dimensions. There are 12 tiles. It's rather complicated, but it's sort of, at the end of the day, it simplifies the question to something you just check. Okay. Except that is CE complete, so it's still not computable. Okay. What about one dimension? One dimension, the situation is that there's a so-called two-tile theorem. Okay, instead of 12 tiles, you only need 2 tiles. Okay, the statement is exactly the same statement, except that the finite graph over here is much easier to describe. The finite graph is this. So here I'm using the parameters 3, 7, and 9. Okay, to specify the 2 tiles. The first tile is called T1, and the second tile is T2. Okay, so T1 is consists of just the 2 like boundary parts with the central part, and the T2 is the 2 boundary parts in the central part. But those boundary parts are eventually going to make the 1, right? You know, because you're going to just identify them, okay, point by point. So the other nodes, I colored them red and blue respectively. So when you it's now possible to actually put these two things into one. Like the resulting graph is very simple. It's just this figure 8 shape thing. Okay. So the boundary ones, the 3 nodes over there become common, right? You know, there are 3 nodes, and then there's the red ones and the blue ones in this order. Okay. So so for one dimension, this is it. Like whether there's a continuous, you know, equivariant map from f of 2 to the z to a subshift of finite type just depends on whether you can actually put, you know, that subshift of finite type, put something over here to respect that subshift of finite type. Okay. But then this further thing, which is nice, is that you can actually further analyze this, and the subshift problem for one dimension is actually computable. So I'm not going to give the details, but there are certain things about the graph combinatorics over there which allow us to actually fully understand this without actually, you know, it's not CE complete anymore. Okay. I want to report one more piece of information, which is that coming back, so this theorem over here, I'm restating the 2 tile theorem, where the 2, 3, and the 4 are exactly the same as before. But now I try to consider the new problem, if you want, the new problem of whether there's a Borel equivariant map from this one-dimensional thing to X. Okay, the 2 over there says there is a continuous equivariant map. But now we can prove that these things are actually equivalent. So if you have a Borel one, you must have a continuous one, and vice versa. Of course, the backward is obvious, but if you have a Borel one, you must have a continuous one. So this proof over here, I realized it recently, and it's a very simple forcing argument. So it's kind of satisfying to say, oh yeah, I mean, it's useful to study set theory. But anyway, this is kind of, in some sense, it's a little surprising because this is sort of the first time that I realized that a Borel problem has a computable answer. Okay. Because if you look at the original problem, there's nothing to be computed. It's, you know, if you compute the obvious definability over there, is like pi 1, sigma 1, 2, or something like that. Okay. So the corollary over here is that the Borel subshift problem is decidable, which is kind of nice. And of course, some of my students are trying to take advantage of this and trying to compute some real problems over there, like chromatic numbers, but it's not easy. So the reason then I realized that some people, Grebic and Rodron, recently also proved something about this. And in fact, that they show that this problem is in p-space. And in fact, they proved that in the most generality, the problem is p-space complete. So that explains why we had a hard time computing this by hand. So, but anyway, I just want to make the statement that there seems to be a lot of connections to what people have done in computer science. The 11 names, if I counted right, over here, are all computer scientists. I know none of them. But according to Grebic and Rodron, like these people have done things that are just a little bit predates us. Like, you know, they consider exactly the same problem, and they proved that this is like decidable. Except that our contribution is now just, we not only know the Borel problem is decidable, but also the Borel problem and the continuous problem are exactly the same. So that is our, their study did not reveal this. Okay. But anyway, if you think about this, we can come back to dimension 2 and we can ask the Borel question, whether they're the same as the continuous question. And the answer is no, because this last thing is not equivalent to the previous 3 statements, simply because you got different answers, right? You have this Borel, the chromatic number questions and the Borel combinatoric chromatic number questions, and the continuous ones have different answers. So you know that these are not equivalent, okay? But this does not say that the Borel question is, in general, of course, we know that this continuous question is CE complete. So, but we do not know that the Borel question is CE. We don't know that. Okay. Anyway, I will just finish with a couple of open problems. The first is we still don't know the full story about dimension n greater than 2. So for 1 and 2, we understand them pretty well. Except that for the Borel question, we still don't have a good question. But for n greater than 2, it seems that the details are so much that it's hard to actually pin down exactly what's going on. And also, what about the other groups? Of course, that's always a legitimate question. Okay. In fact, for some kind of nilpotent group, solvable groups, it's possible that we can have full answers over there. Okay. And this is the question I just mentioned about the dimension 2, the Borel question. We don't know what is the complexity of this problem. Okay. We know that it's different from the continuous question, but we don't know the complexity of it. Okay. Before I finish, I really want to take this opportunity to mention this is one of the greatest problems in dynamical systems. Okay, it's not my problem. It's not even our problem. It's not even a logic problem. It's a problem in dynamical systems. It's talking about the conjugacy between Z subshifts of finite type. Okay, and it's known that in the 70s, it's proven that by, I think, 2 or 3 papers that are published in the Annals of Mathematics and Journal of AMS and things like that. They proved that this problem is CE. Okay. This problem is, computably enumerable, but it's still not known whether this is computable. Okay, up to this day. So some related results early on in 1964, it's very early, that it's already known that the conjugacy relation of this problem, when you replace Z by Z squared, it is undecidable. This already was known. And in 1973, Williams was the person who showed that this problem is CE. He showed that the conjugacy problem between one-sided Z subshifts of finite type is decidable. But we don't know, this difference is very small. Now we're looking at the two-sided subshifts of finite type. And the answer is not known. This has been open for about 50 years. Okay. So I can't help but mentioning this problem. It's one of my favorite problems. Even if it's not, it seems to have to do to do with what we do. So, yeah. Okay. Thank you very much.